YouTube 11.4, we're going to be finding the magnitude of the cross product. And if angle theta is between A and B, it will measure somewhere between 100 and 0 to 180 degrees, or 0 to pi. If that happens, then our magnitude of the cross product, we can find that by taking the magnitude of A times the magnitude of B times the sine of theta. But we have to be given theta in order for this to work. So a geometric representation for this theorem is as follows. Here's vector A, here's vector B. Here's my theta between the two vectors. If I build my parallelogram and I create a projection or an orthogonal projection, that perpendicular line here, that's the height of my parallelogram. Well, if you notice, A, the magnitude of A would be the base of my parallelogram. H, a little trigonometry, sine of theta is equal to H over the magnitude of B. Multiply the magnitude of B over to sine A. There's my height. So in essence, the area of this parallelogram is the magnitude of the cross product vector. Because this is your base, this is your height. So we have like a little bit of a sub-corollary of this theorem. The length of the cross product vector is equal to the area of the parallelogram determined by A and B. The value will be the same. So example 4 says find the area of the parallelogram formed by the points P, which is 1, 4, 6, Q, negative 2, 5, 1, negative 1, and R1, negative 1, 1. So I'm going to make PQ one vector, so negative 2 minus 1, negative 3, 5 minus 4, 1, negative 1 minus 6, negative 7. Then I'm going to make another vector P to R. So R starting 1 minus 1, 0, negative 1 minus 4, negative 5, 1 minus 6, negative 5. So these are my two vectors. Treat them like A and B. So we want to find the magnitude of these two vectors, or the cross product of these two vectors. That will be the area of your parallelogram. So what we have to do is we have to find the cross product. So again, think of your determinant, ijk across the top, negative 3, 1, negative 7, second row, that's your first vector, 0, negative 5, negative 5 across the bottom. Let's go find it by the diagonal method. So I, negative 3, 0, j, 1, negative 5, repeat it out front. Downhill, I times 1 times negative 5, negative 5i. J times negative 7 times 0, that's 0j. K times negative 3 times negative 5, positive 15k. Uphill, 0 times 1, that's already 0k. Minus negative 5 times negative 7 is positive 35, so minus 35i. Minus the next uphill is 15j, so minus 15j. Combine everything together, we get negative 40i minus 15j plus 15k. So find its magnitude. All right, so we'll take and square the negative 40, square the negative 15, square the 15, and then take its square root. Calculator tells me that the inside is 2050. If they want a decimal answer, then we'll type this in and give our answer as a decimal. If they want a simplified radical because it ends in 50, I know 25 is a factor. So 2050 divided by 25 is 82. Really can't break 82 down, but to 2 and 41, there's no more perfect squares there. So 5 times the square root of 82 square units will be my area. Next, we have a special triple product. This is property number 5 that we talked about earlier. This is called the scalar triple product, that A dot B cross C. Well, we can find this real fast. This is the same as if you make a 3 by 3 determinant where now whatever you're doing the dot product vector, that's your first row. Then B cross C, B components is the second row, vector C component is the third row, and now you go ahead and find the determinant. You found that triple product. And what's very interesting is that this triple product becomes the volume of this. We can call it a parallelipid. I've heard people call it a parallelogram prism. Now, however, because your determinants can be a negative value, you'll notice that in my formula, I'm taking the absolute value of this triple product, which means we'll find the determinant and then take its absolute value. And don't get confused, because books will put absolute value bars around your determinant bars, and it looks like double bars and like, oh, am I supposed to find the magnitude? No, you still find a determinant, but it has to be a positive answer. So if we were asked to find the volume of a parallelipid with vector A, B, and C with the following components, here's that double bar determinant, if you will. The outside bars are the absolute value bars, inside bars are for your determinant. Vector A across the row 1, vector B around row 2, vector C across the bottom. Copy your first two columns. We'll start crunching numbers. 3 times 2 times 1 is 6. Negative 5 times negative 2 times 3 is 30. 1 times 0, stop, that's 0. Minus 3 times 2 times 1, minus 6. Minus a negative 6, minus a 0. We can crunch the numbers. We get the absolute value of 36, so the volume of that parallelipid is 36 cubic units. All right, and the last, I had to add this to the notes. Vector A cross B is orthogonal to those vectors, and now we're just going to transpose them into unit vectors, and we're going to talk about some additional properties that we can have. So if you look at my diagram here, treat A like I, B like J, K is the cross product. So K is equal to I cross J. All right, then next, if we put I, think of that as the vertical, right, orthogonal to JK. So that'd be J cross K. And J, that would be K cross I. So if you're looking at how to do this, make up these little cross products. K is pointing up, you always go in a counter clockwise direction, just like you do with angles. So it's I cross J, everything's positive. J cross K, K cross I. If you reverse the order, remember when you switch the order here, then everybody becomes negative. Negative, negative. So if I were to write J cross I, that would be a negative K. I cross K be a negative J. K cross J be a negative I. So there's, if you will, the commutative property of those, giving me those negative unit vectors. And it's also too important to see this, is that if you cross product the vector with itself, these unit vectors, they become 0. So a quick example, I cross I, there's 1, 0, 0, 1, 0, 0, and you can see the 3 downhill products are all 0. The 3 uphill products are all 0, so that will create 0 vectors when you take any of your unit component vectors and cross it with itself. So those properties there, I would like to add these into your properties of cross products. So excuse me, for your test sheet, you might want to have those. So here's an example. They may ask you to simplify this expression into maybe one of your unit vectors. So we can think of I plus j, all right, that's one vector crossed with another vector. So let's look at it in the following fashion. 1, my properties have plus signs up here. Change the minus j to plus a negative j. And now what I'm going to do is I'm going to treat this as my vector being crossed with I and then cross it with negative j. And then I'm going to do this in reverse. So again, same concept here. Here's my I crossed with I plus j. It will be I cross I, j cross I cross negative j, j cross negative j. Well, I cross I, that's the 0 vector. J cross negative j, still the 0 vector. J cross I, that's negative k. I cross negative j, that too will be a negative k. And so we can simplify that to negative 2k. So if you run across a problem like that in homework, we can simplify using those